record this. So it's not a problem that you don't know it, you don't remember it from when you took it. Key is that you learn it now, right? Just learn what you need to learn now. So I'm about to talk about what these pieces and parts are, but just know that these group numbers that I'm circling, they tell you how many electrons in the outer shell. So when you're asking yourself, how many electrons are in this on the outer shell of this, there they are. So there's 3, 4, 5, 6, 7, 8. Now, I know that this says 13, 14, 15, 16, 17, 18. There's a good reason why it does that, but I'm just going to let you know right now, don't worry about it. You're just looking at the ones place of these columns that I just put circles around, and that tells you the electrons in the outer shell. That's it. Just remember that. So if I give you a periodic table and I tell you how, and to help you, just to help you, then you should know that's how many bonds it forms, or how many electrons in the outer shell. So let's talk about it. So there's 2 rules you need to know. 2 rules you need to know to do well, to understand bonding. So bonding, there's 2 rules. Rule number 1, atoms, let's call them elements. Does everybody know what an element is? All right, so elements, and atoms are those elements, tend to move toward being neutral.
I need to see the top 2.
Well, write this down for right now. Neutral means not positive and not negative. 0 charge. So let me be clear. They want to not have a charge. That's rule number 1. That's what neutral means. Is that clear? Is that better? We get that? It's just a simple rule. If you have something that has a positive charge, is it stable? No, because it wants to be not charged. Good. So that's rule number 1. Rule number 2, elements want, I'm going to put want in quotation marks because they don't really want, but they want to be, or to have a full outer shell.
Well, what is the they?
Huh?
What is the
They?
Yeah.
Elements. So let me get rid of they. Elements, atoms, elements, or atoms if you want. Elements are types of atoms. So, well, I guess I'll go over that in a second. But elements are atoms. They want to have a full outer shell, and they want to be neutral. Are we good with those 2 rules? Do we have them written down?
No.
Okay. Say what? Yeah, change they to elements because somebody was confused on what they is. May I go on? All right. I'm going to go on. Is that right? Yeah. All right. So I see people erasing. All right. So the world is made of matter. All matter, the basic unit of matter is something called an atom. There are smaller things, but an atom has a nucleus that has protons. These things are called protons. And they have a positive charge. They have a +1 charge. Is everybody okay with that?
So atoms is
Yes, protons make up atoms. So in the nucleus of an atom is made of protons. I'm just going to put one proton in a minute. And it also has neutrons. So they have these things called neutrons. Neutrons are in the nucleus as well. They have no charge. And atoms have electrons. And electrons have a negative charge. Okay? Everybody all right with that? It's just three things. What do positives do to negatives? Yes, they do. That positive and negative would equal zero charge. Excellent. But what do positive things like magnets or positive or negative charges, they attract? Opposites attract. So yes, they cancel, and they also attract each other. And what do like charges do? Repel. So we got to keep that in mind. That's common. You play with magnets most of your lives, right? You know, when they're opposite, they attract, and when they're the same side, they repel. You can feel the push, right? You played with magnets, correct? So you feel the push. So there's a positive out there in the universe. What's going to happen? What do you think is going to happen? A negative is going to be pulled towards it, right? It's going to be pulled towards it up to a point. There's going to be a point. It's not going to be able to get any closer, and that point is called a shell. This is called an orbital or a shell. Okay, so it's not an orbital, it's a shell. So somewhere in this shell, you're going to find one electron for every proton, and you're going to find that electron going around and around the atom. Just around in that space, somewhere in that space, you're going to find that electron. Now, atoms have many shells. Now, these are shells. These are spaces. There's no wall. Does that make sense? Let me. How can I say this? Has anybody ever gone to another state?
Yeah.
Anybody gone to another country, another state, another city? How about another city? You're driven around the city, and then somebody tells you you're not in Cleveland anymore. You're in Brooklyn, or you're in Lakewood, or you're in Garfield Heights, or you're in Beechwood. Was there a wall? Did you go through a wall?
No.
There probably wasn't even a sign, right? You just drove, and somebody says you're in Beechwood now, right? Well, it's the same here. There's no actual wall. There's no line, okay? But there's a first shell. All atoms have a general form of the nucleus is in the center. And then around it, you have the first shell. That's the first shell. And then you have a second shell. And then you have a third shell. And it keeps getting bigger. As the atoms get bigger, the shells get bigger. Now, do you agree that... All right, so do you understand what I'm saying with the general pattern of an atom? The number of protons define the element. So if you have one proton, by the way, we call that the atomic number. The atomic number is the number of protons. It defines this element. This element, for instance, is hydrogen. How do I know it's hydrogen? How do I know it's hydrogen? Who can tell me based on this statement? Yeah. It has one proton. If it had 2 protons, it would be helium. If it had 3 protons, it'd be lithium. If it had 8 protons, it'd be oxygen. Well, how do I know that? Wait, how do I know the numbers? Well, first of all, I'm an old man. I've been doing this a long time. But if you want to know what element you have when you're given it, you look on the periodic table. What do you see there? What does this say? I know it's blurry. What does it say? Atomic number. 26 is what? For what? Iron. So if there's 26 protons, it's iron. Whatever the number of electrons, whatever the number of neutrons, if you have 26 protons, it's iron. If you have 1 proton, it's hydrogen. No matter what. Is that clear? All the other stuff is irrelevant. The only thing that matters is the number of protons when you want to define the element. Lithium has 3 protons because its atomic number is 3.
You said 1 proton is hydrogen?
See, look, there's hydrogen, and look at it. What is it? 1. 3 protons is lithium, 4 is beryllium, 11 is sodium, 12 is magnesium, 19 is potassium, 20 is calcium. You don't have to memorize it. They tell you on a table. All you got to do is read it. All right, that's it. And because of what I just told you, the number of electrons in the outer shell, they tell you right here. How many electrons in the outer shell of sodium? 1. How many electrons in the outer shell of potassium? 1. How many electrons in the outer shell of calcium? 2, etc. All right. So now let's talk about these rules. There's 2 rules, guys. There's 2 rules, not just 1. It makes sense that you had 1 positive charge. You had hydrogen, 1 single positive charge, no neutrons. It's just sitting there, and you got 1 electron. That makes sense. Like Adam said, they cancel each other. I'm sorry, did you need something?
Yes, where it says the number, whatever, down
Here? You want me to hold it there? Okay, I'll hold it there. Yeah?
Where's the number of protons is on the upper right side of the element?
That's right. It's labeled. If you look at the key, can I go back to the periodic table for a second? All right, just for a second. If we look back to the periodic table, look at the key. Do you see the key? This is the key. Atomic number here. Boom.
So atomic number is the same thing as protein?
That's right. Look here. What did I write here? What did I write? Number of protons to find the element. And what does it say? Atomic number. The atomic number is the number of protons. Are we all good with that idea? Not really. What's off? What's not making sense? Oh, okay. You just need time to write it down. All right. But are we getting the concept so far? All right. So it's kind of makes sense. You have a positive, you can have a negative come and find it. They're going to neutralize each other so you get no charge. This atom right here has no charge. Yeah.
Why wouldn't the negatives come to the positive if they don't have no charge?
Say it again.
Why when the negative proton, when the positive proton and the neutron?
And the proton, the positive and the negative, yeah.
Yeah, and when they come together, why don't have no charge?
It is no charge. They're together. This is it. This is as close as it's going to get to the proton. That's called the first shell. That's as close as it can get. So the first shell is the closest place an electron can get to the proton. And at this stage, this has 0 charge. So we're good with charge. No charge. 1 proton, 1 electron. 1 minus 1 is 0. No charge.
So hydrogen has no charge?
This hydrogen has no charge. This hydrogen has no charge. Because there's 1 proton and there's 1 electron. The only thing that makes it hydrogen is what? You have a proton.
Yeah.
I can take that electron away.
Will it still be a proton?
Yeah. It'd still be hydrogen, but because it's still 1 proton. But I took the electron away, so now it's positively charged.
So how would a neutron look?
Yeah.
I'll have to draw. Let me draw. Hydrogen doesn't really have a neutron, so most hydrogen doesn't have a neutron. So let me draw helium. Helium has 2 protons and 2 neutrons. And then it has 1 shell and there's 2 electrons in it. Yes. I do not, but I have paper towels, and you can go to the restroom and get a tissue, and if you want to go. Okay. So this is what the neutron would look like. There's just 2 neutrons and 2 protons. It's still only plus 2 charge because neutrons have no charge, correct? So it's plus 2 minus 2 equals 0. So this also has no charge. Are we good with that idea?
Wait, what's on the outside?
So the neutrons cancel out the protons.
The neutrons, they just stabilize the nucleus. They have no charge. They have nothing to do with this. And usually I don't draw it. The only thing that has to do with it is isotopes, and that's a story for another day.
What's on the shell?
The shell is just a space.
No, like what's on
It's an electron.
those are electrons?
Those are electrons. Let me redraw it so it's clear. Mr. Mendoza speaking. May I help you? Yes, ma'am. Okay. No problem. As long as she has a pass, no issues. All right. Very good. Bye-bye.
So this is for helium, right? So this is the element helium? Now why I just go up and
Yeah, this would be the element helium. Adam, how do I know this is the element helium?
Because it has 2.
That's right. Look, I look at the periodic table, and it has 2, and it's the element helium. It's all on the periodic table. All you got to do is calm down and read.
Could you make us
It doesn't make sense.
Yes, I'll print one for you, and I wanted to laminate them, but I'll just print them and you can put them.
Wait, did you say
Yeah, do you have a pass? You're good. Go on. I'm gonna print it for everybody. I wanted to print. I took my time because I wanted to print them and laminate them, but it's gonna take too long. So I'm just gonna print them and hand them out. You can put them in your binder. Yeah. Say what? No, you just have to hold on to it. We're not there yet. Yeah. Yes, just sign out and sign back and sign the pass back in when you bring it back. Oh, someone's already gone, dear. You have to wait till they come back. Is it an emergency? I don't know what to do. Well, the rule is only one person at a time. If it's an absolute emergency, wow, we're losing our minds right now. We're losing our time.
Wait,
Our time is slipping.
so does every element have like, do any elements share the same amount of protons?
No, very good question. No. All elements have their own number of protons. I'm gonna say this again. I'm glad it's sinking into some people's heads. I fear that some people are not. It's still not being. The consequences of what I'm saying are not processing in your brains. But let me be clear. 1 proton, it's hydrogen. If it has 28 protons, it's nickel. 29 protons, it's copper. If it has 47 protons, it's silver. 79 protons, it's gold. If it's 6 protons, it's carbon. 5, it's boron. 7, it's nitrogen. 8, it's oxygen. Each element has its own specific number of protons that if you change it, you change the element. In nature, they don't change anywhere but in the sun, in a star. In the star is the only place the number of protons changes. In the middle of the sun.
It has its own protons.
What?
Wait, say it again? Each element has its own what?
Number of protons.
Sir,
Yeah.
the patient behind you, your wife.
Yes.
Let me see.
Where?
Wait, did you answer the question, what's the atom? He said each element.
Yeah, I did.
I just put atom is made of proton.
No. An atom is made of what? An atom is made of what? I just drew it on here 3 times. It's made of a nucleus, The nucleus has protons and neutrons. Protons and neutrons. That's the nucleus. And then it's a bunch of electrons in the shells around it. So protons, neutrons, and electrons, that's when the atom is made up. The number of protons defines the element. Everybody here knows there's a difference between iron and gold.
Yes.
The fundamental difference is the number of protons. Everything else is a consequence of that. Still conversations going on, and it's probably the reason I've had to repeat myself in some cases 3 or 4 times. Yes.
Did you say for every proton there's one electron?
No, I didn't say that. I said there are protons, neutrons, and electrons. We're about to talk about that question. I'd like to talk about this part of the question. How do you know how many electrons something has, and when? And that goes back to these 2 rules. Are you ready? Mm-hmm. So you have an element like hydrogen. Okay, it has 1 electron. I hear people talking. I wish that people were more interested in trying to figure out what's going on. So I'm going to go ahead and just get rid of the H because I usually draw an H, but I'll put 1 positive charge and I'll call it hydrogen. Now there's something else you should know. Some more information. By the way, this is the first shell. Like the borders between a state, there is no line. All right? So the first shell can hold 2 electrons. The first shell can hold 2 electrons. Are we good? Yeah. The first shell can hold 2 electrons. Every other shell can hold 8 electrons. Is that clear? Mm-hmm. That's it. So shell 2, 3, 4, 5, 6, 7, 8 can all hold 8 each, 8 electrons each. The first shell can only hold 2. I think that makes sense. Tell me when you put your pencils down, I'll know that you're done writing. So I hope you wrote that down. Poor kid looks tired. So the first shell is the closest shell to the atom. Let's go back to this drawing. I think it makes sense that this shell is going to hold less than the rest because the circle's smaller. Okay, so the first shell can only hold 2. So here's hydrogen. The first shell. Is it neutral? There's 2 rules. Rule 1: is it neutral? And the answer is yes, it is. How do I know? I have 1 positive charge and 1 negative charge. 1 minus 1 is 0. Are we get that? Okay. Yeah. Anybody else? Sure. The first shell is for hydrogen's filling in the first shell. Is it neutral? We said yes. Because there's 1 positive minus a negative is 0, no charge. So it is neutral. We're good. So the first rule is set. No problem. Second rule is, does it have a full outer shell? How many electrons can that outer shell hold? This is the first shell, so it can hold 2. How many does it have? 1. So is it full? No. So wait a minute. If it's not full, why don't we fill it? Why don't we put another electron in it? You want to do it? Yeah. So if we go ahead and put another electron in there, because that would make it a full, but now it's what? What's 1 minus 2? -1. So this would have a -1 charge. That's no good. We can't do that. Because it's breaking the first rule. Man, what's an atom going to do? How do we get both of these rules? Yeah, to work. Say what? Make another shell. That's a really good idea. That's not what happens, but it's a good idea. Right? You could put another shell, and then you could add some more electrons there, but then it would be more negative. But it's still a good idea to see if it would work. Yeah.
Can you let the next person go to the bathroom? You take it forever because I gotta go to it.
There's like 20 people on
Who went to the restroom?
The boy who sat at the end of the thing, he always said,
Okay. Let's let it go. Here's a second pass. The next person go. There. Problem solved. Just go. Take care of it. No conversations necessary. Thank you. Moving on. Oxygen. Let's take a look at a problem. There's these 2 hydrogens. They both have that same problem. Let's look at oxygen. Oxygen has 8 protons. I'm going to put, you know what? Let me just draw it so you can see it. So 8 protons. So 1, 2, 3, 4, 5, 6, 7, 8. 8 protons. And I'm going to put a neutron in blue. It has 8 neutrons too.
Holy moly.
How many neutrons?
8. 8 neutrons. The neutrons don't impact the problem, but you should know they're there in the nucleus.
sir, why not just turn on?
That's right. I would draw it.
That plant real?
Yes, ma'am.
Oh, thought it was fake. It looked fake.
And a lot of people think that. So, the first... no, really. A lot of people... I had a kid argue with me. I'm like, it's real. Huh?
Right, what
It is
is
a,
it?
it is a palm tree, yeah.
What's real?
How you got a palm tree
That
here?
tree back there.
That's not a tree.
Oh my... Okay, can we let it go? It's a palm tree. Let's move on. Talk to me after class if you want. So, in the first shell... How many electrons do I have to have if it's going to be neutral, if we're going to solve number 1? 8. I have to have 8. That's right. Good. So the first shell has 2.
Yeah,
The first shell has 2, because how many can a first shell hold? Only 2. Somebody said it. Only 2. So first shell can hold 2. How many does this atom need? 8. So we got 2. So how many in the outer shell? So there's 4 out here. No, it's not 4. 8. We need 8 total. We took care of 2 of them. How many more do we have to have? 6. So 1, 2, 3, 4,
Wait, can there be a negative charge in the main circle?
5, 6. You mean in the nucleus?
Yeah.
No, the protons are the only ones in the nucleus. Good question.
There are neutrons in there too.
The neutrons have no charge. Isn't there a difference between no charge and a negative charge?
Yeah.
Okay, so, but it's a good question. So these are paired, there's 2, 4, 5, 4, 5,
what is
and
it's
6.
not the blue thing.
It's an N. The neutrons, N for neutron. So now we have 2 shells because we needed the space. We know we needed 8 electrons. We had 8 because we had 8 protons. We're trying to get this first rule satisfied. The first rule says it has to be neutral. If we have 8 plus charges, we need 8 negative charges. The negative charges have to be in the shell. They can't be in the nucleus. What? Let's just talk. Let's just move on. The whys I can answer after class. I can't answer that, but we're going to answer them after class. Adam, focus. Doesn't matter. Move. If something's distracting you, move. So, going on. This is this is oxygen when it's neutral. When oxygen is neutral, does it have a full outer shell? Because it needs, how many does it need in the outer shell? 8. It only has 6. It has 2 in the inner shell, you're right, but it doesn't have 8 in the outer shell. It needs 8 in the outer shell to be satisfied, but it can't take 2 more, because if it took 2 more, then it'd have a negative 2 charge. And it doesn't want to be negative. And why? Because it's unstable. As soon as it's negative, it gets attracted to something else, and something else takes what they have. They can't have that charge, because they'll find something and they'll react to it. So that's the short answer of why, Adam. The question then is, what is this atom going to do? How are you going to get both neutral and a full outer shell? Well, to answer that, you have to understand this, what sharing is. Take the hoods off. We're not allowed to have hoods on in the building. So what does sharing mean? A lot of people think that if I'm sharing this pencil with the...
About
time.
All right, leave him alone, please. It's his business. Unfair, not funny. Leave it alone. Focusing. If my wife and I, we share a house, who owns the house? Both people own the house. Shh. So what happens is these atoms share electrons. These atoms share electrons. Those of you not listening, I see you. You're the ones that are going to be confused. I'm letting you know this is key. But these atoms share electrons. So when we look at this, what happens is that these 2 electrons will be shared, and these 2 electrons will be shared. They're sharing them. So when they share electrons, how many electrons does this atom now have? 1, 2. That's 2. Because it's sharing these 2. Sharing means they both own it. These are electrons. So so this atom has 2, this hydrogen has 2 electrons, but it doesn't get the charge. It gets to share the electrons, but not the charge. Is it time to go? No.
My
Stop.
paper say 4 to 5.
Stop. The principal's clearly stated that you have to leave at 48. She sent out a message just yesterday reminding the teachers that we're leaving at 48. We're moving on. I'm not wasting any more class time. You're not understanding. You're in the middle of understanding a very key concept. You're seeing a bunch of lines on a molecule, and you don't understand what a molecule is yet because you don't understand what sharing electrons means. But you're more worried about leaving.
I'm sorry, sir.
No, I'm not talking about you. I'm talking about the class in general. So the key here is that they're sharing these 2 electrons. So this atom now has a full outer shell. These 2 have a full outer shell. But they don't have a charge. Win-win. Both of the rules are satisfied by sharing. That's why atoms share electrons. That's how they form bonds.
That's how you get a full share.
That's how they get a full shell and not get a charge. So now let's take a look. Let's look at oxygen. Let's count. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in the outer shell, full outer shell, no charge. What do we call this thing I just drew?
Oh, I got a question.
Wait, before you do, I want to hear. These are bonds. That's right. These are covalent bonds. But what is this molecule? No, oxygen is the element. This is oxygen. Oxygen with 2 hydrogens. What is it? Water. That is water. 2 bonds. 2 bonds being shared. All right, I had to delete this, and unfortunately, there was it did delete a section because it was trying to make it shorter for y'all, and it deleted too much. So I have to try to summarize what we talked about. So we said there's 5 functional groups that we talked about. First is hydroxide. It's OH. Secondly, the second group they may be a different order on your paper, is COOH, or a carboxyl group, and that's a C double bond O and OH. All right, so that's a carboxyl group. 3 is an amine group, which is an NH2. So it's 2 bonds between them. And the fourth is a phosphate group with a P with an oxygen connected to hydroxide, connected to hydroxide, connected to hydroxide. So there's, and the fifth is a sulfhydryl group, which is basically just a sulfur and a hydrogen connected to each other. And why don't you just do it now? Oh, just do it Thursday morning or Friday morning. Put it there. Leave that there. All right. So when we're talking about biological molecules, you have these things, again, they're called functional groups. Now, this is known as hydroxide. This is known as a carboxyl group. Let me leave those brackets off and just say carboxyl or carboxylic acid. All right. This one is known as an amine group. This is a phosphate. This is sulfhydryl. So those are the 5 basic. There's many more, but just looking at these, if you get these, you'll be fine. These are monomers of glucose, and the monomers include many more monomers. Remembering that when we talk about the word monomer, we're talking about the single units that are put together to form a larger molecule. And the example we used in class was the Lego blocks being put together, right, to form something bigger. Well, when it comes to carbohydrates, it is the monosaccharides that are the Lego blocks or the units for anything that forms something larger than the unit. So when you're looking at trying to form something with carbohydrates, you're going to be made with monosaccharides. These are three of them. There's a couple more that I talked about in class, and there's many more that we're not going to talk about. But glucose, galactose, and fructose are three of the big ones. There's also ribose, which we'll talk about when we talk about nucleic acids on Thursday after the lab. So when we're looking at carbohydrates, one of the main ideas here is that the functional unit that every carbon has on it in a carbohydrate is a hydroxide group. So you'll notice that every carbon has hydroxide except the one that's linked in whose oxygen is being used to link. And so you'll see here that every one of these has an OH group, and that OH group is what we call hydroxide. The difference between the three of these, and we had spent time, you guys, discussing it and trying to figure this out, but the difference between them is how you link them together. So if that second to last carbon with the OH group gets linked with this carbon here, then you form what's called a fructose molecule. Notice so what I'm talking about is that if I were going to draw these out in a chain, it would be a carbon with two hydrogens, and there'd be a hydroxide sticking out, and then that would be connected to a carbon with a hydroxide, and that would also be connected to a hydrogen. You'll notice that not all the hydrogens are drawn in there in those drawings. That's to be expected. So what I'm doing is I'm drawing this out, these 6 carbon sugar chains out here. Okay, so the third carbon is going to have all the carbons have hydroxides on them. All the carbons have, and there's 6 carbons, 3, 4, 5, 6. They all have hydroxides on them. That's what makes one of the things about. And of course, they have to have 4 bonds. All right, the two ends of the chain have 2 hydrogens. Now, what we could do is we can take and use this oxygen, circle around, and connect it to a carbon. Use an oxygen, come around and connect it to carbon. Now, oxygen can only make 2 bonds, and one of the bonds is here to this hydrogen. So if this oxygen is going to circle around and make a bond with this carbon, the second carbon, you see here, this is the oxygen that's coming around. At the end, it's going to make a bond with the second carbon. If it comes around and makes a bond with the second carbon, then it's going to, let's say, attack this carbon. Then the only way that could work, because this has 4 bonds already, is for OH to leave. So then this oxygen can then bond to this carbon. But this oxygen already has 2 bonds, one to hydrogen, one to carbon. So the only way it can bond to this carbon is this OH to leave and this H to leave. So that would mean that water leaves, H2O leaves. And what you form then, because now you have this oxygen bonding to this carbon, you form this pentagon. So it comes around, and so that oxygen that used to have a hydrogen on it and connected to carbon, it's still connected to carbon, But now it's connected to another carbon, to this carbon here, all right? And that carbon, of course, still has its, it still has another carbon connected to it, which has an OH group and 2 hydrogens. So this here is this here, okay? And then the connections keep going. The connections keep going. So you have this carbon then is connected to another carbon. It still has its OH group. It's connected to a hydrogen. These don't change. And the shape that it makes, and the reason it makes that shape, it's because of intermolecular forces, and there's all kinds of conversations of how what a molecule's basic what a molecule's shape is. And what we can do is we can draw it like this, CH, just to save space on the drawing. And of course it still has this hydroxide, and it goes up, and it's bonded to a carbon that has a hydrogen. Now there's 6 carbons, so this was the first carbon. Let me number them. This is 1. It's the same as this one here. This is 2. This is the same one as here. This is 3. It's the same one as here. This is 4. It's the same one as here. This is 5. The same one as here. Now, of course, 5 still is connected, as I said, to the 6th carbon. And that has, and they write it in the diagram as H2OH. And that hangs out here, and this is your 6th carbon. So each carbon in the chain, depending, if you close the chain this way, then you have a 5-sided sugar with 1 carbon and OH group sticking up here, 1 carbon OH group sticking up here. But if you closed it to the first carbon, if you closed, instead of the second carbon, if you close it to the first carbon, instead of the second, now notice here, these other two, instead of closing closing the ring on the second carbon, close on the first carbon, then what you end up with, so in other words, if this attack from this oxygen goes to the first carbon instead of the second, then you form a 6-ring structure. So here's the oxygen. Let me do it in red. Here's your oxygen connected to carbon. That carbon is not the second, but the first, which is connected to carbon, which is connected to, there you go, which is connected to carbon, which is connected to carbon, which is connected to carbon, which is connected to a carbon, and that is carbon 1, 2, 3, 4, 5, and 6. Now, of course, as I said earlier, each carbon has a hydroxide. This carbon's hydroxide was used to close the circle. All the rest of them still have their OH groups. And where the OH groups go help define which monosaccharide you have. So again, remembering that all of these, the OH is on the, let's say, outside. All these OH groups are to the outside. I think the third carbon, you have 1. And of course, you have 4 carbon or 4 bonds. So I could fill in the hydrogens the way I'm doing here, or you can just assume that they're there the way they do in the diagram. Regardless, there's 4 hydrogens. They're actually at specific angles, and that becomes important. Organic chemistry. But there you have it. That would be the carbon. Those are the two different rings, and whether this third carbon has the OH moving this direction or that direction gives you one galactose or glucose. Fructose forms a 5-ring structure, but they all have 6 carbons. It's just a matter of where those bonds are made. Remembering that each carbon can only make 4 bonds, and that and those bonds are sharing electrons. So you can connect those two monosaccharides together. Let's put together two glucose or a glucose and galactose, like we said in class, and where they connect is important. And I'm not gonna worry too much about all that. I'll just say they're connected. One's glucose and one's galactose. The question is, these two together form something called lactose, and that's a disaccharide. So the word is disaccharide, or 2 sugars to form 1 sugar. So it's a 2 sugar. So it's a dimer, right? It's not a polymer. Poly means many. Oligo, or let me say this. Di means 2, and oligo means a few. All right. So when you see oligosaccharide, that means a few saccharides, not as many as many, and many could be thousands long. Oligo could just be 8 or 9. All right. So it's just about these prefixes just give you a hint as to how many you're dealing with. So in order to break this up, as we discussed in class, you need an enzyme, and the enzyme has to fit the enzyme has to fit the substrate. So if this is glucose, and this is galactose, they go in as the pair, they go in as lactose, and when they're done, the enzyme is not used up in the reaction. The enzyme helps the reaction go quickly. As I said in class, what you're dealing with here is a substance. These bonded sugars are very long lasting.
Whoa!
And the example.
Sir, put her down.
Okay, let me pause. I can't believe I have to do this. I'm trying to get this done. Alrighty then. Now that that's settled, let's go back to trying to get this done before the class. I'm sorry that I had to redo all these notes. Can't stand when errors happen. So what happens? The enzyme is not used up. The enzyme really doesn't change much at all. But what you end up with is 2 products where you started with 1 reactant. The thing that binds to the enzyme, is called a substrate. The enzyme is called an enzyme. And the products are the products. So glucose and galactose are the products. The enzyme doesn't change, as you can see.
Nobody is totally.
As you can see, the enzyme doesn't change, but you started your substrate in the beginning. The substrate was, in this case, lactose, remembering that OSE means sugar. That's the sugar that is lactated by mammals. The product that you end with is glucose and galactose, remembering that the enzyme in this example that will be tested and we have discussed numerous times is called lactase. If it ends with ASE, it means enzyme. If it ends with OSE, it means sugar. So you started with a disaccharide and a glucose and galactose bonded together, chemically bonded together. You end up with glucose and galactose as a product. So people that are lactose intolerant are lacking the lactase, the enzyme. So they can't drink milk because milk has lactose in it. And if they ate it, their stomach would be very upset because the bacteria in their intestines would make a lot of gas, and the gas would put pressure on their abdomen. Not to mention other impacts like diarrhea, etc. So lactose intolerance means that you're not producing enough of this enzyme called lactase. So lipids are another one of the biomolecules. If we zoom in here, we start off with you not having this, but now you have it. So let's take a look at this, and then I'll draw it out. And when I draw it on the board, I would draw it in your notes. So in this lipid section, you see here, you see that it has this molecule called glycerol, a very important molecule. You're going to see it a lot this year. It's 3 carbons long. It's real simple. It's a simple molecule. It's an alcohol. That's why it says OL. If you ever see OL ending something, it means alcohol. Okay? So then you have this glycerol. Do you see that these two that this became this? Do you see how they're similar? There are some differences that might confuse you. There's some differences that might confuse you. For instance, this says CH2. See CH2. This has the hydrogens drawn. Do you see the difference? This is still CH2. Do you understand that? Right? We said we went over chemical bonding, right? We know that this carbon needs to make 4 bonds, right? We know that one of the bonds is going to this oxygen, one of the bonds going to this hydrogen, one of the other bonds going to this hydrogen, then the 4th bond's going to this carbon. You see here, this also has 4 bonds. 2 of the bonds go to 1 to each hydrogen, as you see here, then 1 to this oxygen and 1 to this carbon. This is shorthand for this. It's like initials. These are like initials, and this is like the full drawing. Is that clear? But they're the same thing. Now, there's another functional group that we said was acids. What functional group did we say was an acid? Look in your notes. You should have reflected. Again, every day, you wait till next week to memorize these things, you're not going to do well. Functional groups, there were 5 of them. Which of the 5 functional groups was called an acid? Which of the 5 functional groups was called an acid? Carboxylic acid is correct. Very good. Now this carboxylic acid, what was its shape? What were the atoms involved? And how were they connected? You drew them, right? You put them on index cards because I gave you these 5 things. I gave you 5 in a high school pre-AP biology class. I gave you 5 things to memorize. They did. You can. They double check. I think they did. So the question is, the point is, you were told you have 5 things to know by this week. That was last week. They were hydroxide, carboxylic acid, amine, sulfhydryl, and phosphate. Those 5 things. Do you remember them? If you don't have them written down, you better watch this video earlier in the video and make sure you have those down. I would write them on index cards or write them multiple times and know what I'm looking at. Because you guys that are looking at this and not understanding what you're seeing, I bet you, I would bet money, there's a good group of you that are looking at all these letters and like, what the heck is this saying? I don't understand. I know that's going on. The reason you're feeling that is you're not doing your half the work. You've got to know what you're looking at. The only way to do that is to practice those terms. Yeah. Give me a second. So can somebody tell me what carboxyl group should have? That's correct. COOH. COOH. C double bond O, single bond OH. That's what you should have in a carboxyl group. So let's see if we can find this. Like I said, let's see if we can find Waldo, right? C, let me zoom in here. C, still, huh? Let me increase the width of that. So C, double bond O, single bond O. The H left, you'll see why in a little bit. The H left, C double bond OH, that would be a carboxylic acid. The H is left and it's now connected to the glycerol. We'll look at how we did that in a little bit. So there's 3 carboxylic acids. Do you all agree? Do you all see that? Yeah. Because these are all carboxylic acid groups. There's not all one. This is a carboxylic acid group. This is a carboxylic acid group. This is a carboxylic acid group. Right? 3 carboxylic acids. This is just a bunch of carbons and hydrogens. Do you see them? All carbon connected to carbon. It's just a chain. No. Do you see any oxygens here? No oxygens. None. So these things are called. Unfortunately, I have no. These things are called fats. Fats. Because they have a long chain of carbons and there's no oxygen. Do you see there's no oxygen, correct? Yeah. So if there were oxygens in it, there might be something else. But just this long chain of carbons. If you have a long chain of carbons, we call them fats. So when you say fat, what you're really talking about is the long chain of carbons. Is that clear to everybody? That's it. That's all there is to it there. So this is a fat connected to an acid. What do you think we call it? Fatty acid. Thank you. And that's all it. That's it. It's not that hard. There's 3 of them. This is one. Here's one fatty acid. Here's one fatty acid. Here's another fatty acid. And here's a third fatty acid. 3 fatty acids connected to a glycerol. 3 fatty acids connected to glycerol using the carboxyl group. What do you think we call it when you treat 3 fatty acids connected to a glycerol? What do you think we're going to call it? It is a lipid, but what do we call it? Read, think. 3 fatty acids. What is the number 3? What's the prefix for 3? Tri. Or triple is fine, but the prefix is tri, T-R-I. And then there's glycer. So it's a triglyceride. So when you go to a doctor and they do a blood test and they're looking for triglycerides, they're looking to see how many of these you have in your bloodstream and the quality of them. We'll look at the quality in just a minute. So this part here, the glycerol is always going to be the same. This chain can be different. This chain of carbon and hydrogen can be different. Now, what I'm writing is a summary that you should be writing on the left-hand side of your page, or perhaps you write at the bottom. I don't know, depending on where you are in your note-taking. A long chain of carbon and hydrogen. That's what a fat is. Now let's take a look at this long chain, these long chains. What is the difference between these three long chains? Look at them and tell me, do you see any, let me zoom in a little more maybe. There, what is the difference between these three? You have them in front of you too in the handout. What differences can you see between those three long chains? So some are longer than others. Very good. Okay. What else? There's another big difference.
Is it like, there's one like where does it have
Yeah.
Some have two and then some have three.
Two what?
Two hydrogens. You know,
You mean this three? Yeah, we'll look at why that is in a minute. Anything else?
What the, alright, well, like,
oh, I see it. Some
They have
of them
different-
have
Some of them don't have double bonds.
That's right. Some of them have double bonds. These have double bonds. And some have no double bonds. Look, there's no double bonds here. None at all. So that is a big deal. Let's look at why that is. Now, if I were you, I would put little arrows on my molecules just to make sure I knew on my fats, just make sure I remember that there's no double bonds. Putting the arrows not enough. What I would do if I were taking notes, say double bond, double bond, and I like doing it in color, I would write no double bond. So when I go back to review this material and to recite it, I know I can look at it and tell without going to too much more effort, because I know I have 7 classes and I know I got to get all this in my head before the end of the test. I can review my notes because they're organized, because they're well labeled, because I wrote down my reduction. I have the main idea written down. I know I can just flip through it, review it. Or maybe I make index cards because that's the way I like to do it. And I go over those again and again and again until I get it firmly in my mind. And I test myself. Do I know the difference between the fatty acids? Can I tell which ones have double bonds and which ones don't? Can I tell which one's the glycerol, which one's the fat, which one's the fatty acid? Do I know that this, even though that's a fat, do I understand that this whole thing here, including the carboxyl group, is a fatty acid? Do I get that? Those are questions you have to ask yourself. And don't come into class next week, tomorrow. Don't leave class with saying, I don't know. I just don't know. That's not good enough. Like, if you don't know, you ask. You go into tutoring. You write it down. You look it up. You ask me, or you ask a colleague, or you ask a tutor. You look it up. You get ready for your job, which is to pass that test next week. Now let's go ahead and take a look at this fatty acid. Let's take a look at carbon, double bonded oxygen, single bonded oxygen, and a hydrogen. How many bonds is that? 3. How many does carbon need? 4. 4 is correct. 4 is correct. So it needs to be connected to another carbon. Well, we know this is a carbon chain, right? So let's count how many carbons we have. 1, 2, wait, let's count this one too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 18 carbons. So I'm just going to go ahead and draw them out. There's so many, I can't do 18, Mr. Miller. You can write 18 carbons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. There's 18 carbons. That's the chain written out. How many bonds per carbon?
4.
So this carbon has 2 used up already, correct? How many hydrogens could it have? What's the max? 2. It can only hold 2 because each hydrogen is going to use 1. 1, 2. 1, 2. 1, 2. 1, 2. You should be drawing it with me. 1, 2. 1, 2. Does it annoy you that I keep saying that?
Yeah.
Do you want me to stop? Yeah, and when I had Destiny over here, I would have kept going when you said it annoyed me. It annoyed you. Is that correct, Destiny? As soon as you said would annoy me, it would encourage me to do it more. Yeah, because you guys annoyed me so much, I had to get you back somehow. I'm a human being. No, you just annoyed me. Yes, I am petty. I told you that like day one. I'm a petty person. I said it. I said I'm very petty. All right. So that's all those carbons. What about this last carbon? How many hydrogens does it need? All right, if I put 2, let's go ahead and put 2. Yeah, I need 3 because there's 4 bonds. So what you're looking at here is something called a saturated fatty acid. This is saturated. What do I mean by that? Every carbon, not including, obviously, this is the acid part, right? Carboxylic acid. I'm going to put Ca. Not including the acid part. Every carbon here is full of hydrogens. They're full of hydrogens. And so because they're full of hydrogens, another word for full is saturated. All the bonds are filled with a hydrogen. So we call it a saturated. This is called, another word for this fatty acid is a saturated fatty acid. That's it. Have you ever heard of fatty, saturated, and unsaturated fats? You've heard of those, I'm sure. You can see them in labels. This is what a saturated fat looks like. And there's consequences to that. I'm going to show you why that's important. I don't just want you to memorize it. I want you to understand what the implications are. Now, it turns out that a double bond is shorter than a single bond. Now, if you had a robot that had one leg shorter than the other, do you know what would happen? It would walk fine. It could, assuming it doesn't fall over. Good point. It would walk in a circle. Every step, it would take one big, or at least in a curve, right? Because it would always, one leg would take bigger strides than the other, and you'd always end up going in a corner. So when a bond is shorter than the rest, it turns, it bends. It bends the molecule. So 1, 2, 3, 4, 5. So if we had to put a double bond in this, obviously you're probably not going to want to draw this out, so just pay attention. You have the double bonds drawn in there, but they're not showing you. They're not showing you the twist. So I'm going to show you the twist here for a reason. So they're going to form a double bond, but it's shorter, so they're going to get closer together. What needs to happen, though, for you to make a bond between these two carbons? A double bond. So this carbon has 3 already, and this carbon has 3. If they're both going to make double bonds to each other, there's 2 bonds. What do they have to get rid of? One of the hydrogens each, right? You have to get rid of a hydrogen, otherwise you can't make the bond because it doesn't have the space. So what you end up with is this. Now let's go ahead and take a look at the diagram that you have and see how they drew it. Let's take a look at their drawing. Oh, shoot. Look at it. Do you see that this is CH? This is CH2, but now this is CH, and this is CH? It's missing a hydrogen. Why? Because each carbon can only make 4 bonds. So it bends. Now, why is that important? Well, by the way, we call this an unsaturated fatty acid. And this unsaturated fatty acid is not full of hydrogens. It's missing two. Here they are. They're missing. This bond is shorter, so it bends. Now, there's a consequence to that. Let's talk about it. And you all know it. In fact, you all know the difference between saturated and unsaturated fatty acids. You know it. You've seen it your whole life. You just didn't know why it was that way. So, I'm assuming everyone in here has at least seen meat being cooked. I know some of us are vegans, but you've at least seen meat being cooked. And how many people here have washed dishes at home? I wash them at home now. I used to when I was a kid. You guys don't wash dishes?
I have a maid.
Oh, you do? That's nice. Do you wash dishes? Have you seen your mom wash dishes?
Destiny.
You've never watched your mother wash dishes?
My brother wants to do this.
All right, have you seen your brother wash the dishes? All right, what about that young lady back there? Have you seen someone wash dishes before? Okay. He has never washed dishes. It's so sad. Hey, look, it's good to be the youngest. All right, here's what I'm gonna say to you. Here's what I watched this my whole life. Here's my point. Just as an aside, this is not a story, but this is just a fact. You better start learning some of these behaviors. I would learn how to at least know how to wash dishes. It sounds easy, but it ain't. If you ever eat off a plate that someone doesn't know, you're gonna find how to wash dishes. You're gonna find little food scraps on it. You'll take a cup and there'll be soap in it. It's just you can do washing dishes wrong. Okay, so make sure you know how to wash this. Never. So anyways, moving on, focusing. So here's what I'm saying to you. You know, you've seen this before. If you've seen your parents or brother or mother or father, grandparent or somebody cook a steak, a pork chop. Who likes steaks? Who likes pork chops? Sausages? Any of these? Bacon. You don't like any meat? You've never eaten meat? Have you? Okay. So have you seen someone cook it? Okay. And have you had to wash the dishes afterwards? Oh, not everybody has. You know, some people grow up in a vegan home. They have never eaten a Buddhist. No, I'm not talking about her. It's not talking about her. There are people that are Buddhists that never killed. They don't kill animals. They don't eat animals. It's just not a thing. All right, focusing. So my point is, not everybody has. That's why I asked the question. I'm not joking. So you cook a steak, and it starts sizzling. Right? It smells to me amazing, especially if you have a little garlic and salt and pepper on it. So you cook it, you take it off the plate, it's all nice, you eat it, you cut it up, you're eating it. Now it's time to wash the dishes. When you get back to the pan's cold. Is it still all kinds of oily? No. What's left in that pan? Fat. And what is it? Is it liquid? No, it's a solid, right? It's a solid. It's kind of like a gel, right? It's a white. And by the way, you should just take a paper towel and swipe it clean and then throw it away. Otherwise, your sink will start stopping up with fat because that fat will coagulate in the pipes, and you'll have to call a plumber to clean out your pipes. So just collect it with a paper towel. Throw that saturated fat into the, huh? So these saturated fatty acids are straight. They're straight. And because they're straight, they can lay down on top of each other and form a solid. Remember, a solid, the only difference between a solid and a liquid is how much space is in between the molecules. In a solid, the molecules are very close together. So in a saturated fat, the molecules can get real close together. And so they form a solid. You know this. You've eaten butter before. Butter at room temperature is not liquid. It's solid. Right? Solid. Butter, animal fat, your own fat is at room temperature a solid. Why? Because animals make saturated fats. Now, plants, the vegans among us and vegetarians, plants have unsaturated fatty acids, and these unsaturated fatty acids have a kink to them. So they push off. They don't, and that's too big a kink, but they have just this twist to them, and because they're a twist, they can't lay down next to each other easily. It takes that, even if they have just a little bit of kinetic energy, they move around each other, they push away from each other. And so they are liquid. So saturated fats are solid at room temperature. And unsaturated fats are liquid at room temperature. So that's why corn oil, olive oil, sunflower seed oil, canola oil has some saturated fats. So that's why it's kind of like coconut oil. You'll see it's almost like animal fat because there's saturated fat in it. But olive oil, corn oil, sunflower seed oil, it's all unsaturated fats. So what is it at room temperature? It's liquid. You can pour it out of a bottle. It's a liquid. Why is it a liquid? Because it's made of unsaturated fats. Most plant fats are unsaturated fats. Now, why is that a bad thing or a good thing? First of all, you need all kinds of fats in your diet. You do. You don't have to eat animal fat to get saturated fats. You can get saturated fats from vegetables. But obviously, animal fat's a good place to get saturated fats. The problem is you can't eat too much. If you eat too much of it, this is what happens. You have an artery or a vein. Some of these arteries are pretty big. Some are smaller. And when you have a lot of saturated fats in your bloodstream, when there's a lot of them, what happens is that your body processes them. Now, they're already laying down one on top. they're starting to form little semi-solids in your blood, globules, and they start to form these, your body changes them and they start to form these plaques. A plaque is like a buildup. When you go to the dentist and they scrape it off your teeth. Yes, I'm getting there. Yeah. You know how you go to the dentist and they scrape your teeth? They're scraping plaque off your teeth. That's this like kind of solid, brittle stuff. And it builds up on the inside of the artery. What is an artery or vein carrying? What does it transport? Blood. So it starts to make the hole smaller. So little by little, over time, not overnight. It's not like you eat a steak and all of a sudden you got this problem. Over time, there's this buildup. They can get real clogged. It's a clog in the pipe. The pipe is an artery or vein, but it's a clog. Does that make sense to you? That's a plaque inside your artery or vein. Well, what's that doing to your blood pressure? What is it, when you have a hose and you have water shooting through your hose, you put your thumb over the opening, what does that do to the water pressure? It raises it, increases it, and lets you shoot the water further, right?
Isn't it raising?
That's right, it's raising the blood pressure. Good.
So I was gonna say.
The buildup, the blue is the buildup of the plaque buildup.
But is it like raising because like the blood is like pushing on
That's
the,
a cute.
on the artery?
Well, the blood's still trying to get, your heart's pumping. Your heart's, you need blood. Your body needs the oxygen in the blood to live. So your heart is pumping. And your heart is trying to pump the blood, P-L-A-Q-U-E, plaque. And your heart is trying to pump this blood through this space, but the space is smaller. So your blood pressure goes up. BP goes up. You get high blood pressure, in part, it could happen because you're decreasing the space inside the blood vessels, so you can't push through enough blood through that smaller opening. So you have to push more, you have to push it harder, so that increases blood pressure. That could lead to all kinds of problems. But then what happens, and this is the kicker, then what happens is that some people get bruised. You bump into the table, your dog jumps on you, your big brother punches you in the arm, you get hit with a book bag by accident on the bus, whatever. You get a bruise. A bruise is it means you're bleeding. So what does your body do? You studied it during feedback mechanisms. Your body starts to form blood clots to stop it from bleeding. That's a good thing. But now you have a blood clot that's in your bloodstream and it's trying to get through the bloodstream because it gets knocked loose. What's going to happen when this big old blood clot tries to get through the space? It's not going to get through. It's going to get stuck. And when it gets stuck, the blood doesn't go to that part of your body. If that happens in your heart, you have a heart attack. If that happens in your brain, it's called a stroke. If it happens in your lungs, it's called a pulmonary embolism. It happens in the kidney, you get kidney disease. It happens in the liver, you get liver disease. So this clogging, all this because of the difference in fats that are in your triglycerides in your blood. That's why doctors measure the triglyceride in your blood. Because they want to see how much of a risk you have of having high blood pressure, of having what's called artery disease, right? When they call it hardening of the arteries, because you start layering in that plaque. So that's why they're concerned about that. And by the way, African Americans and Hispanics, we have a bigger problem now. Is it because we eat more fatty foods? Possibly. Is it because of lifestyle, our cultures? I think most people agree that African American, Hispanic cultures, we focus on eating meat, right? I mean, you go to a barbecue, they don't have broccoli on the grill. So eating that meat means eating saturated fats. Eating saturated fats means a higher percent chance of this happening. So is that the problem? I don't know. I don't know if anybody knows. It could be genetic. It could be environmental. In other words, it could be choices we're making. It could be we have to eat better because we have an increased risk. So whatever. So fats. Now let's go ahead and go on to proteins. How much time do we have left? How many minutes? 4. All right. So I'm going to stop here, and I'll finish this. I'll post it, and you can watch it for homework. Now, hear me, because I can see right now I saw at least 3 people's eyes go. Homework? I'm not doing that. Okay, don't. But tomorrow you got class, and you're expected to know these things. I'm going to go over amino acids. It's really important that you understand all 4 of these. You're going to have to break these down tomorrow. You're going to have to watch a video. The more work, if you put 15 minutes worth of work in tonight, it could save you a lot of frustration tomorrow. So I would I'm not kidding you, about 15 minutes, maybe 20 minutes tonight on this video. Obviously, you're going to fast forward to where you need to go. I'll even make little chapters to say, protein, fats. You don't have to watch the whole thing. I would suggest strongly, and I'm giving this, you know what? Let me take it back. Instead of making suggestions, I'm being silly. Let me make this a homework assignment. It'll be due tomorrow in that box that says 6th period. I expect notes labeled with dates, a date, today's date, for proteins. The rest of this video that I'm going to post tonight. And we'll make it, what do you think is fair for 20 minutes worth of evening? 100 points, 50 points. Which do you think, 100 or 50?
100 and 100.
1,000 is too much. Huh? 100 points then. This is worth 100 points. Watch it tonight. Take the notes. You can watch it on your phones. Safety contracts I'll collect tomorrow. Anybody here not do the safety test? Watch the video and look at the first 5 in the beginning. So, okay, that takes care of lipids. Now, when we're looking at proteins, you're looking at these. These are now so for each one of these, so with each of these, with carbohydrates, the monomer was a monosaccharide. So one of these, or ribose, which isn't listed, or some of the other oses. These single sugars that you can link together to form a chain. These lipids don't form polymers, but you do kind of take fats and attach them to things. You're still doing something similar. It's just they don't really do polymers. Now, when you're looking at proteins, now they also have these monomers, right? So the nucleic acids, proteins, and carbohydrates all form polymers using these monomers, these little Lego blocks. Remember, they're like Lego blocks. In proteins, it's amino acids. They look like this. This is an amino acid. So let's go ahead and draw it and see what amino acid, when you link them together, what it looks like. So when we're looking at an amino acid, you have to remember you're going to have an amine group. It's an N with 2 H's. Those are one of the 5 functional groups you have to know. And then that's connected to a central carbon. So there's a carbon in the center. That is connected to let me use a thicker line. That is connected to an R group. An R group is a variable. So a variable can change. So depending on what you have, you can change it. So then you have H carbon has to have 4 bonds. One of the bonds is always to hydrogen. But finally, you have a carboxylic acid group. So you have a carbon double bonded to an oxygen, single bonded to an oxygen, and a hydrogen. So this is a carboxylic acid group. This is your amine group. And together, they form an amino acid. That is the building block, the Lego that you're going to use to put together to make a bunch of amino acids put together to make a peptide. So let's talk about what that is. You have NH2, and then you have a carbon, then you have some R group, which is a variable. It can be any number of 20. By the way, there's 20 different ones found in humans commonly. There's more than 20, but there's 20 common ones found in the human body, in our foods. And that is what an amino acid looks like, and we've already identified the different groups. So now let's put some of these together. If we take, let's put a big old bunch of them together. And see what happens. How is it that we can put these together using our bonding rules, keeping in mind that we have to keep our rules. The rules don't change. So you have a bunch of different amino acids. Now they're different. Why are they different? Because the R groups can be different. You have an R1, might be a small group. R2 might be a big group. You may have another R1 here. Maybe this is R18. Remember, there's 20 different ones. Maybe this is R2. And maybe this is R20, right? Each one of these groups is a different, have different qualities. Some are big, some are small, some are acidic, some are basic. Like there's just a bunch of different qualities to each R group. So now the question is, how do we link them together? If I want to connect this carbon to this nitrogen, this carbon already has 4 bonds. It can only make 4 bonds. Nitrogen has 3, can only make 3. So how do I connect these two? I have to get rid of something. And what I'm going to get rid of is this OH and this H. Now what happens when you put OH and H together? When they come out, what OH plus an H equals H2, why 2? Because there's 2 H's, O. So this is water. Water's coming out. Now water coming out, you're going to get, at each time you connect one of these amino acids in the chain, so when this amino acid is connected to this one, you're also going to get water coming out. When this amino acid is connected to this one, you're also going to get water coming out. So each of these, you're going to get water coming out. So every time you combine these, every time you add a link in the chain, water's coming out. Why? Because you have to get, in order to allow them to make bonds, because carbon can only make 4 bonds, in order to make those bonds, you have to get rid of this bond to this oxygen, and nitrogen can only make 3, so you get rid of this bond to this hydrogen. That happens at every end. So let's go ahead and do it. Let me go ahead and make that change. This one goes out, makes water, and then you form a bond. I'll put it in red here. And again, this one, we could follow the electrons if you wanted to and see how they do it. And they would twist and turn, but the geometry might be a little different than what we're looking at here. But the point is that these water H2O leaves, and that allows for the carbon to bond to the nitrogen. So again, repeated again, and the carbon bonds to the nitrogen. And repeat it again, and the carbon bonds to the nitrogen. These bonds that you see here that we just made between the carbon that used to be a carboxyl group, and the nitrogen that used to be an amine group, and the hydrogen of one and the hydroxide of the other combine to make water. Those are called peptide bonds. Peptide bonds. When you put a bond, anytime you're connecting these are called peptide bonds. They're the bonds between the amino acids. They're what hold the amino acids together in a chain. And they're the sharing of electrons between the carbon of one amino acid and the nitrogen of the other. So if you have, anytime you take two amino acids, instead of drawing them out this way, I'm just going to write amino acid 1, if you don't mind. That's represented by, this represents this whole thing right here. And I connect it to another amino acid, and I'm going to put, to keep it simple, amino acid 2. As soon as I connect them, they become a peptide. And because there's two amino acids, we call it a dipeptide. Again, all having to do with the bond between the carbon of one amino acid and the nitrogen of the other. Now, if I have a bunch of these put together, one connected to another, connected to another, and they could be hundreds of amino acids long, then we would call this a polypeptide. Polypeptide is a bunch of amino acids that are lined up one after the other. And the R group can be different. So here again, you can have an R group that is big, and so that's R group 1, and maybe amino acid 2 has an R group 3, and maybe amino acid 3 has an R group that is different, and maybe the amino acid 4 has the same R group. So each different, how many amino acids you have, it gives you the quality of that protein. The change in amino acid can make a big change in the polypeptide, which then would change the protein. A protein is one or more polypeptides make a protein. Let's take a look at an example really quickly. So on Thursday, we're going to have a lab. It's mainly observational. We're going to look and see, you're going to make some observations and say, did it work or not? What did you learn from it? That kind of thing. We've talked about it already, but I'm going to kind of walk you through it right in a second. And then about half the day, that should take about half the day on Thursday or Friday if I have you on Friday. It's the same thing. And then then the second half of the day, we're going to go over nucleic acids. But now let's go and talk about the lab. A rundown for Thursday's lab. I will not be here tomorrow. You will have an activity. You all learned, look, you've all learned very well, I think, by this point. If you don't put anything away, listen to what I'm saying. If you don't do the work in class, guys, you probably won't get the work done. You're here, you're in class, you have an activity, do the activity. Okay? All right. Wait, before you go, Thursday, you're going to take in a Tupperware box, you're gonna take, could you all listen to me before you go anywhere? Look at the board. You're gonna take this battery and you're gonna have a plus and a minus, and you're gonna put a test tube around this battery terminal, and you're gonna put a test tube around this battery terminal. This is gonna be salt water, and it's a battery. What's gonna happen between these poles? There's gonna be a charge. You're gonna have electricity. I wish you'd watch, because you're going to be confused on Thursday if you're not watching, you're not paying attention. Electricity. So the electricity is going to take and it's going to break the water up. H2O will get broken up into hydrogen gas and oxygen gas. Now remember, we balanced this equation, and we know that it has to be how much oxygen gas do we expect to get as compared to hydrogen gas? 2 to 1. 2 to 1 ratios. Oxygen without that, before it's bonded, has a negative charge, so it's going to be attracted over here to the positive. So the oxygen is going to go here. O negative is going to go here. The hydrogen is going to have a positive charge, so it's going to go towards the negative. It's going to go over here. So as the gas is made, what happens to the water? The bubbles are made. That's a gas. What happens to the water? It gets pushed down. So what we'll see is the oxygen come down here, and the hydrogen is going to come down twice as far. Why does it come down twice as far? Because you expect 2 times the amount in the test tube. And then you've separated water, and then we can blow them up and make water back again. Make sure you have your safety test done. Make sure you have your safety contracts. The safety test? Then that'll be one thing. That'll be something you do tomorrow. Where's my... Well, I don't know what we're going to do. I guess we'll have to do it. What'd you say? I did it with every other class, but you guys... Let me give you